Hi there, my name is Ben Blatt. And for the sake of the students, I'm going to go by Mr. Blatt. And today we're going to be learning a lesson about the area of parallelograms that are not rectangles and squares. So, hi class, welcome in. We have some problems to start working on to practice our knowledge of areas of shapes that we've already started learning. Um, Does anyone remember the area, how to calculate the area of a rectangle? That's right, length times width. And so I'm going to put up on the screen right now uh, some problems that I want you to solve. Some of them might be a little bit challenging, and it's important to read the instructions first. So we're finding the area of specifically the shaded portions of the rectangle. So I'm going to give you 5 minutes to find the area of these rectangles or shapes that are composed of rectangles by giving you the length and the width. And then we're going to discuss our answers together and maybe talk about how we can use this information to learn more about different types of parallelograms and talk again about what a parallelogram is. Hopefully everyone can see what I just shared on the screen. If not, let me know in the chat or raise your hand in the meeting window. And again, the area is the length times the width of the rectangle, and those are both provided here. So you have 5 minutes to complete these. So once the students were done with their 5 minutes, I would form a formative assessment by going through each of the rectangle calculations and asking every student what their either understanding was, how they calculated it, and what their answers were. I would start with the three easiest ones, which would be the yellow, the red, and the gray, which are just simple by the book length times width multiplication. I feel like the two that might trip students up would be the blue diamond, which is technically a square, and they might say that's not a rectangle, that's a square, or potentially even more likely, they might say that's a diamond, not a rectangle, and then just I could explain to them, well, I said these are all rectangles. That means that all four of those corners must be 90-degree angles, and that technically a square is a rectangle, and just because it's rotated uh, on its axis does not mean that it is not a rectangle. As far as the uh, plum colored shape is concerned, I think this is where there might be some more students that get a little tripped up. And then I would remind them that we are only searching for the area, the shaded area. And so one way that we would do that, class, is, and first, again, I would ask a student to be able to explain this to me. But if students were too tripped up by it, I would take over and explain. So class, what we have here is, let's imagine that there wasn't that white portion in the middle. All we need to know is if that entire purple rectangle was completely together, completely intact, how would we calculate it? And I would call on a student, and hopefully they answered. Well, we would do 6 times 11, and then we'd say, great. What is that area? And then someone would I would call on a student, and they'd provide 66 if the student who didn't answer, who gave the answer initially, did not provide one. And I would say, well, now we've removed some of that area. So we had an area of 66. What area did we remove? And then I assume, I believe it is likely that one or many, if not all students would say, oh, we removed a rectangle of uh, a length and width of 5 and 2. And then I would say, well, what's the area of a rectangle that has a length and width of 5 and 2? To which they would answer 10. And we'd say, okay, well, we have this purple rectangle, and its area is 66, and we know the missing portion is what size? And I would call on someone, and they would say 10. And so I would say, so we had 66, and we removed how much? 10. That leaves us with an area of, and then the students should at that point be able to point us to an area of 56. So I think we have a good handle on calculating the area of rectangles, which are parallelograms. They just happen to have 90-degree angles in the corners. A square is also, which was that blue diamond that we looked at, is also technically a rectangle and a parallelogram. Today we're going to discuss finding the area of other types of parallelograms. But before that, I just want to kind of get into why that formula works and maybe some real world examples. And so the first thing is, why do we even need to know the square units or the square footage or the square inches or the acres? An acre is a square, it's an amount of square feet. I think it's like 43,000 square feet. Why do we need to know the square units of various shapes? And at this point, I would prompt the class by hopefully someone's raised their hand already. And then if not, I'm not going to random call a student, but I'd say, what about something that maybe covers the floors? And hopefully I get some hands. If I don't, then I'll random call a student and say, what's something that we have in schools and businesses and houses that cover floors? And that student will say carpets. I'll say, how did this house that has a carpet in it know not to buy an entire warehouse worth of carpet? And hopefully that prompts the student to say, oh, they needed to know the measurement of the floor. And that measurement, of course, is square units. And so then I want to say, okay, so we know that there are real world applications to this entire thing, and that is for the square units in things that tend to be rectangular, such as rooms. But what about paint? And hopefully students will say, well, those go on rectangular walls. And then I would prompt them to say, well, you have you don't always have rectangular walls. Think about houses that have a staircase in them, and the wall that goes underneath the staircase. Is it always a rectangle? And some students will go, oh no, some walls beneath staircases are actually diagonal. And so we'll discuss that it's not always as simple as just saying, I know the width and I know the length. And today we're going to do some discovery into figuring out how to find different formulas for that. Today is going to be parallelograms, and then tomorrow is actually going to be triangles. So the first thing is, I just want to say, why does that formula work? So we're going to take a look right now at a rectangle. And so we say, all right, we've already covered this before, but I just want to see if everyone remembers the length times the width. This says 3 times 4. So what's the area of this? And I'm going to call on someone. And 12, that's correct. So that's 12 units squared. This could be feet. It could be whatever. It could be 12 square feet. It could be 12 units squared. How do we know that there are 12 squares in here exactly? And we can visualize this. We don't need to get into complicated mathematical proofs, although there are tons of them out there. We can just say, like, well, we know from this side that it's got a length of 3. So we're going to chop that up into 3 units of length. And then down here, we've got 4. So I'm going to chop that up into 4 units of length. So before going through this entire thing, does anyone in the class see where this is headed? And if someone raises their hand, see if they can explain it. And if they can, great, and we'll fill it in as they're explaining it. And if not, I'll be like, all right. So the first thing I'm going to do is just pick something to extend out. We're cutting a tray of brownies, okay? We know that we've been promised that this tray of brownies is going to give us 12 square brownies. So we're going to try. And we know we're going to cut this side into 3 rows and this side into 4 columns. And that's where we get the 3 times 4. So we're just going to try it once. So that's 1 row. I'm going to then just cut out my 4 brownies. Perfect. Now I have 4 square brownies, and then this entire chunk up here. We don't even have to cut it. We could at this point kind of see with our mind that there's 8 more brownies in here. And how do we know that? Because if we already said there's going to be 3 rows, and we know that this row gets cut into 4 columns, these rows get cut into 4 columns, we've already shown down here that we end up getting 4 brownies of it from the first row. So in the second row, you're going to have the exact same thing. And then in the third row, you have the exact same thing. So basically, we've just said we have 3 rows of 4 columns. That gets us 12 square units, 12 square brownies, 12 square inches, whatever you want to, whatever we were measuring. So now we're going to talk about a different case. It's a little more interesting. So real quick, I'm going to draw a bunch of parallel lines and then crossing lines to make a huge grid. And we're going to pretend that this grid is infinite. It covers the entire universe. It just keeps going out forever and ever and ever. And this is the square units of the universe. And we know we could fit a rectangle at some of these points, and then we would just be able to count how many units are in there. We'd also be able to do the math by saying how many units up is it and how many units over is it. But what we're going to do here is something a little different. I'll put one right here, put one right here, put one right here, and 2 over right there. Now we have a parallelogram. Here's a problem. We know how many units over this is. It starts on that corner, ends on that corner. That's exactly 4. It's exactly 4 up here. We do not know how long this side is, because it does not go straight up these 3 units. It crosses over and has to extend a little bit further to meet over there. And so even though we can say this is a square unit and that's a square unit and that is and that is and that is, we can see it, right? We can see these squares in here. What we can't say is that this is a square unit. We can see that that's a piece of a square unit, but we don't know what size piece that is. It could be 2/3. It could be 3/4. But without magic or without a formula, we actually can't look at that and just guess. So I'm going to bring up some slides that hopefully we can figure out what the formula is for figuring this out. And I'm going to have you guys participate. And if we can't figure it out, I'm going to let you know. And then you're going to see that figuring out the area of a parallelogram is just as simple as the other things you've learned before. Okay, so we have our parallelogram up on the screen, and as we discussed before, we still have the width down here that's supposed to line up down here at the corner. It's not exact, but it's pretty close. But the one thing we don't have, like we would have in a rectangle, is the length. The length would come down here. Instead, we have this line, which is not the exact same quote-unquote length as this one. So what we need to do is figure out, is there a clever way that we can figure out what the area is? Again, we could count many of these squares like this one, or this one, or this one, and get pretty close to an area. But once we get to a square like this, we only have a little portion of area there, and it's not exactly something that, we're not trying to eyeball it. We're trying to mathematically find out what the exact area of this parallelogram is. So does anyone have any ideas of how we might do that? So we asked the class, and maybe I get an idea, maybe not. Maybe someone guesses the right answer, which is the height times the base. If they guess the right answer, I'm going to ask why, and maybe they know. And if they do, then I'm going to say exactly right, and then we're going to move on to this next slide over here, which is that first, before going to the next slide, I'm going to prompt the students to ask, do you see any like hidden tricks or any hidden shapes that exist in this parallelogram that might help us figure out what the area is? And again, that's if they were unsuccessful in figuring it out before. This is something that once it jumps out, you go, yes, of course. But the first time you're learning it, you don't necessarily see how it works. So we're going to move on to the next slide. And we're going to show them that there were two hidden triangles. So we come back over here and we say, okay, there is a triangle that's right here. And it happens to perfectly fit this triangle right here. So what happens when we look at this one? We move the blue outlined triangle, this guy, we cut it off, and we kind of tape it on over here. And so when we do that, we have a different way of calculating this shape. Even though we don't know this length, we can take this triangle and put it over here, and now we don't have to calculate this length. We just created another rectangle, and that rectangle has something called a height, which is this line that goes at a 90-degree angle from one of the bases of the parallelogram to the opposing corner. So in this instance, it's outside of the parallelogram right here. We have this right angle, and we just draw a line straight down to that corner. And now we know that the base, which is from corner to corner, times the height, is equal to the square units of this parallelogram. And we know that because we basically just created a rectangle out of the parallelogram. Now, at this point in the class, on my whiteboard, I'm just going to, again, it would be a larger whiteboard or even in Google Meets, would start drawing parallelograms for them and then include the altitude or height, and this one's 4, and the base, which is 8. It's an infinity because I drew it sideways. And I would do a few of these and start calling on students to tell me, how large this is. In fact, sometimes I might even include the actual length of this side, which we'll call 6, and make sure that students aren't doing 8 times 6, but instead doing 8 times the height, which is 8 times 4, and then hopefully they get the answer of 32. And we're going to do about 5 of these problems. After that, we're going to move on to our online math workbook, and we're going to do, for 10 minutes, 2 pages of that. And at the end of that, I'm going to have a random call-outs to ask people to share what their answers are and see if there's anyone who's having difficulty at that point. And if not, then we're going to move on to the third page of in the online math workbook and have everyone complete that. And they'll have 5 minutes to do that as well. And then again, we're going to go over the answers to those problems. If there's enough time remaining in the class, we'll tease the following day's lesson and how we might discover the area of a triangle. And I'll hint to them that it's related. I hint to the students that it's related to how we discovered the area of a non-rectangular parallelogram. And then for the end of the lesson, we're going to have something that might work as an exit ticket. And what I want them to do is come up with one rhombus problem on their own. So there will be a worksheet that the top question is draw a parallelogram problem and provide your answer. And then the second portion of it is fill in, you have a choice, either something from today's lesson that really confused you or you still don't understand, or fill in something that you found very interesting. And so that provides a few different paths for me to go down once I receive what all those answers are. For all the students who say they're confused about something, that provides me the opportunity to go back and see if maybe I led them a little bit astray, or maybe the penny just hasn't dropped yet. In which case, I can communicate with them by email if it's something that's minor that just requires a little clearing up. It might be something that requires me to provide them a better online resource, or even free up some time to have a private Google Meet with them. And for those who decide to respond back with, "Oh, here's something that was really interesting," or something that I really do understand and enjoy about what we learned today, I either find out that there were a lot of kids who really understood what was going on, or find out that there were not a lot of kids that understood what was going on. And if that's the case, then that prepares me for next lesson to be able to do a little heavier review. But I also might get answers from kids who very confidently answer, "Oh, I thought XYZ was very interesting," and whatever they provide me isn't correct. And then I know that I might need to gently correct that student, keep them very excited about what they learned, but also let them know that that might not be something that is uh, technically correct. So I know a lot of this wasn't specific lesson. Some of it was, but without students here, it's difficult to provide that perfectly. So if you have any questions, please let me know.